Hello students, welcome to my class. In today's class, we will learn a new concept, class 10 circles. In class 9, you have already learned about circles and related theorems. In today's class, we will learn more about circles. So what is a circle? Circle is a collection of points in a plane which are at an equal distance from a fixed point. So, if this is the fixed point, then this fixed point we will call as center of a circle, and the fixed distance we will call as the radius of a circle. So, circle is the collection of all points in a plane which are at an equal distance from a fixed point. Now, we will see in detail the situation arises when a circle and a line are given in a plane. So we will see now. Suppose if we have a circle and a line. We have a circle with a center O and a line PQ. Circle and a line are given in a plane. Then there will be three possibilities. First one, case 1, this is the first possibility. Here the line and the circle will not have a common point. In this case, we will call the line PQ as non-intersecting line. We will call the line PQ as non-intersecting line. Now we will see the next case, case 2. Here the line will intersect the circle at a point, single point. Here the line PQ intersect the circle at one point. Here we will call the line PQ as tangent of the circle. So tangent is a line which have one common point with the circle, which have intersecting with the circle at one single point. That is called a tangent. Now we will see the third case. Here we have a circle and the line line PQ intersect the circle in two different points. If you are taking these 2 points as R and S. So here the line PQ and the circle have 2 points in common. So in this case we will call the line PQ as the secant of a circle. So these are the 3 possibilities we can see when we are given a circle and a line in a plane. The first case, the circle and line will not have a common point. In that case, we will call PQ as a non-intersecting line. In the second case, the circle and the line will have only one point as common. In that case, we will call the line as tangent of the circle. And the third case, the line and the circle will have 2 points in common. And we will call that line as the secant of the circle. Now, we will see more about tangent. How many tangents we can draw for a circle from a point on the circle? So consider a circle with the center O. Here we have a point P. So how many tangents you can draw through the point P? So it is only one tangent is possible through a point on a circle. Next case, we will see, we will consider a circle with the center O and we are taking a point outside the circle. Exterior P is a point, external point of the circle. From this point, we can draw 2 tangents to a circle. So here, we will get to 2 tangents. So from an external point to a circle, we can draw 2 tangents. And the point where the tangent touches the circle, this point is called a point of contact. This point is called a point of contact. Now, what is the length of a tangent? So, length of a tangent is the segment of the tangent. Actually, this is a line. This tangent is a line. So, here the length of the tangent is segment the tangent from the external point to the point of contact. So this measurement, this is called the length of the tangent. So this segment's length is called the length of the tangent. Now we will see some theorems. Theorem 10.1. The tangent at any point of a circle is perpendicular to the radius through the point of contact. This is the first theorem. So here given, what is given? We have a circle. We have a circle with the center O, and we have a tangent. XY is a tangent. XY is a tangent of the circle, and P is the point of contact. So we have given a circle. We have given a circle with center O, and XY is the tangent with P as the point of contact. Now what we have to prove here is the radius, tangent at any point is perpendicular to the radius through the point of contact. So we have to prove that OP is perpendicular to XY. So we have to prove OP perpendicular to XY. So for this, we will take a point Q on the line XY other than P. We will consider a point Q on the line XY, tangent XY other than P. Now if you see, we will join this line, this points OQ. We will join the point OQ. So construction, we are taking a point Q on the line XY and we are joining the points OQ. Join OQ. Now if you see, this point Q must lie outside the circle. Why? Because if Q lies inside the circle, actually Q is a point on the tangent XY. If Q lies inside the circle, then the tangent will become a secant to the circle. So it is not possible. So Q must lie outside the circle. Since Q is outside the circle, this OQ distance will be greater than the radius. So this point where the line OQ intersect the circle, we will take that point as R. So we can write OQ length will be greater than OR. OR is radius. But you know that OR and OP are radius. So we can write OQ is greater than OP or OP less than OQ. We will get OP less than OQ. OP is smaller than OQ. This happens for any point on the line XY other than P. If you consider another point S on the line XY, again that point will be outside the circle. So we will get the same statement, OP is less than OS. So what we are getting is OP is the shortest distance. OP is the shortest distance of point O to the line XY. So we got here OP is the shortest distance of the point O to line XY. But we know that the shortest perpendicular distance is the shortest distance. So we can write OP is perpendicular to XY. So this is how you have to prove first theorem. Theorem 10.2. The length of tangents drawn from an external point to a circle are equal. So, you know already I have explained, from an external point to a circle we can draw two tangents. So, the length of these two tangents are equal. So, we are going to prove this. For that we have a circle. Consider a circle with the center O, and we will take P as an external point. From P we are drawing two tangents to the circle. So we are drawing two tangents to the circle, and the point of contact we will denote as A and P. So we have a point, external point P, and PA and PB are two tangents. So we will write given a circle with the center O, a circle with the center O, and PA and PB are two tangents from the external point, two tangents from the external point P to the circle. Now we have to prove here, what we have to prove, the length of the tangents are equal. That is, we have to prove PA is equal to PB. So PA is equal to PB. For this, we have to do some construction. We will join construction. We will join OP we will join, then OA and OB we will join. So construction, join OP, OA and OB. Now if you see proof, we will see the proof now. Here we got two triangles. We have two triangles. We will consider these two triangles, that is triangle OAP and triangle OBP. We will consider these two triangles. Here this angle is 90 degree because we have already seen this in the previous theorem. The tangent is perpendicular to the radius through the point of contact. So this angle is 90 degree and similarly this angle is also 90 degree. So we will get angle OAP is equal to angle OBP is equal to 90 degree by the previous theorem. Now if you see OP is equal to OP, common side for both the triangles. So this is nothing but the hypotenuse. So this is nothing but the hypotenuse. Now if you see the OA and OB, OA and OB are the radius. So these are the radii of the circle. So what we got is one angle and hypotenuse and one side. So by RHS congruence we can say that triangle OAP is congruent to triangle OBP. Triangle OBP. So we can say that by RHS congruent the two triangles are congruent. So we can say PA is equal to PB by CPCT. Corresponding parts of congruent triangle. So we can say that PA is equal to PB, and we will get another point also we can see here. These two angles also will be equal because CPCT, that is angle APO. Angle APO is equal to angle BPO. These two angles are equal, or we can say that the line OP is the angle bisector for angle APB. So this line OP is the angle bisector of angle APB. In the next video, we will see some example question based on this concept. Thank you, students.